Peer review due date is next Wednesday. So review the instructions there and what that entails. It's mainly to ensure you've started writing something and have a pretty decent rough draft that someone's checked so that you can make it even better and get a even higher score. Because I've learned that generally what you'll have ready by next Wednesday gets turned into me if I make it the due date. And it's, everybody seems to tell me they have ideas that they would have changed or done better after I grade it. Well, this is your chance to find it out first. And also, to get credit, you have to have someone peer review it and make some constructive criticism comments on a hard copy that you're going to bring and show me that you've signed. That's all written down in the instructions. Make those useful. I mean, help your friend. Tell them the good things and the bad things. What doesn't make sense? They want to know. Plus, I hope that this will help you by getting some feedback and reading someone else's. You'll learn ideas of what you want to do to change yours also. So it'll be even better. You can get even better scores. But that's next Wednesday to get the points for that peer review due date. Then the following week, it's due. So you'll have a week to revise after that. But from today, it's due in 2 weeks. And that's the final. Nothing after that. You've had all semester. So review those instructions. I know it might seem like a lot, but read all that stuff. Because that's what I'm grading you on and what I expect. And what most people tend to mess up on, you can read it and catch yourself before you turn it in. So I tried to lay it out there for you. Any questions about the paper? All right. Let's review with some clicker questions a few things about heat transfer then. Put it on the right channel and we'll be good to go. While this is coming up too, I looked about an hour or two ago, and in the first homework of this unit, while you're logging in, only 5 of the whole class have even looked at the answer keys. And of the last homework that was due, 1 person's bothered to look at the answer keys. I'll be blunt. If you don't understand how those are working, or the explanations, the solutions, then it's kind of your own fault because you haven't even gone to look. That's a good way to review and check yourself if you understand those. And I can see who's looked at the solutions and who haven't. Okay. If something's hot, what type of waves does it radiate, relatively speaking? So we learned, as we review, the temperature of something is proportional to the wavelength of light it gives off. The hotter something is, what type of wave does it give off, or at least where the region it peaks in? Are they shorter, longer, or low frequencies? Or none of that? Give you a chance real fast to get your answer in. How many of you have ever looked through binoculars or telescope at stars? Very many of you? Oh, less than I thought. But yeah, next time, especially when you have it zoomed in, you can see the color differences between them a lot better in an instrument. And you can think back of this. You got red stars, blue stars, orange stars, white stars. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We still had 2 people that didn't vote. Okay. 74 short wavelengths. You're right. So the hotter something is, the higher energy waves it gives off, and those are vibrating more quickly. We say they have a higher frequency. That's what we're going to be doing next unit. But that means they're shorter waves. Shorter waves. So the blue and purple side of the spectrum, visible spectrum, have shorter wavelengths. What's beyond blue and purple? What's even shorter wavelengths? You got ultraviolet. Yeah, that's how you remember it. Blue, purple, violet, ultraviolet. We can't see those, but those have even shorter waves. How about on the other end? Orange, red, infrared. Yeah. How about beyond that? What are some other forms of light we can't see? Gamma rays. Gamma light. Yeah, those are really short. That's the highest energy we know of. What else? Microwaves. Yep, they're shorter than visible light, less than gamma. Good. Radio waves. Yeah, not sound, but the radio waves that your radio picks up. Yeah, and those are longer wavelengths. That's longer than infrared. What else? X-rays. Yeah, those are shorter wavelengths than visible. Let's see, did we miss any? Some people, TV, radio, microwave. I think we got them all. Okay, next. All right, so given that, which one's hottest? What type of star? Red, blue, white? Or I didn't tell you enough. You guys vote. I'm getting hand lotion. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. A little longer because the lotion's not in. Okay. And the consensus is white. Oh, good for you. That's not right. He's wrong. Yeah, he's wrong. It's white. Because white includes blue. But it also has the other. And that's what I told you before. So he's messed up a few others. I got to fix that. Okay, good. You guys understand that. This one. All right, go. Your pizza's cool. You stick it in the oven. How would we classify that pizza? A cool pizza in a hot oven. What's the pizza? This is that interplay between giving off radiation and absorbing radiation. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Somebody doesn't want to play. There we go. Most of you think A. Few of you both. Okay, the answer is A. Is it going to heat up? Without using the heat word, is it going to get hotter? Yes. The only way for something to get hotter, it means it has to absorb more than it gives off. Those of you that did C are probably thinking it's doing both. That's correct. It's absorbing radiation at the same time it's emitting radiation. If they're in balance, then it's in equilibrium, its temperature doesn't change. But putting a cold pizza in a hot oven, the point is to heat your pizza up, make it hotter, cook it. So it's a net absorber. With me? And I chose one more to ask you. If you're going, huh? This is the greenhouse effect idea. Basically, it's telling you short waves can pass through glass. Well, what about once they get into your car? Then what happens? Can they make it back out? Do they get trapped? Does it depend? Some people get stuck on opaque, especially non-English speakers. Opaque means it can't get through. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Alrighty. Split, but most of you are going with B. So we got some more explaining to do here. It's the short waves can get in our atmosphere through glass. Then what happens to those waves once they make it in? What can they do? I couldn't. Yeah.
They can get absorbed.
They can get absorbed. True, and that'll heat up the earth or your vinyl interior. Some of them can reflect around too, some bounce off, but they can't make it back through the glass or our atmosphere because they're longer waves after they're absorbed, right? Think of the sun. The sun's really hot. So because it's hotter, it's going to give relatively shorter waves. They can get through. Once they get absorbed, they cause you to heat up. They make you warmer. So you give off waves. But they're not as short as the sun waves because you're not as hot as the sun. So they're longer waves and they can't make it back through. So they stay trapped. So that's why it's A. B, for those of you who chose to see, opaque to the same light that is reflected from an interior surface. A wave that reflects doesn't get absorbed and re-emitted, right? So it's still the same wave. It just bounces off. So a short wave from the sun can get in. If it hits a mirror, for an extreme case, then it bounces off. It's still short, so it could make it back out. So waves that reflect can escape, but those that absorb re-emit longer waves, and those are trapped. I like this question because it emphasizes that.
Does the frequency change?
If the wavelength changes, well, in this case, yes. Yes. And that's our next unit. Generally, when wavelength changes, so does the frequency. If the wavelength gets longer, it's vibrating more slowly. So a bigger wavelength is a slower frequency, and vice versa. The key there is the wave speed is the same. Those three are connected, and we'll have a guide to thinking or an equation for that next unit. Okay, you can put your clickers away. I want to open it up to you at the moment. Questions or concerns of things you've looked through up to this point? Things that are still confusing to you or you've looked at? Past homework? What do you got? Anything you would like me to sort out? I know how it is. Nobody started studying yet, right? It's not till Friday. It's not like this is the only thing you do in your lives, I know. So, but help me out. Is this more because you haven't given it much thought or things you feel pretty good about up till now? I hope it's more the latter, but that's good. All right, some friendly suggestions as you study is friendly reminder. The book has lots of check your understanding questions throughout the reading, and he provides the answers. Those are excellent to make sure you understand. Make sure you know the homework questions I asked and their solutions. Almost all of the odd questions at the back of each chapter are given in the back of the book. So if you want more practice to try to figure this out, like I think I'm getting it, but I always bomb on the test, try a few more out. You can contact me. We still have our TA that is being underutilized. Her office hours are posted on WebAssign. Those are my suggestions. Okay then. Let me know if something pops up though. Yeah.
When we talked about, I think it was Bernoulli, like you have water in a big pipe and then it goes into a little pipe.
Yeah.
You said it's
That's correct, Ron. Kind of like that. So that's, for convenience, let's say this is a pipe full of water. But this works with any constriction for a fluid. So air going over the top of a hill or past a house, it gets constricted. And so it's flowing along. Your book talks about streamlines. And yeah, they get squished here. Like this one might make it through. But these are getting deflected and squished. Not to scale, but you get the idea. So they do something like that. Bernoulli's principle states that when they get smaller, they go through a, well, I should back up. That's the continuity equation. That was the area times the velocity is staying constant. The cross-sectional area. So here it's big, and here it's small. For water to get through and maintain the flow rate, the same amount of water is going to get through. Here, a lot of it can pass, so it doesn't need to go as fast. Here, where it's constricted, in order to keep the same flow, it's got to go faster. So it speeds up here. And now Bernoulli's principle is that where a fluid is moving more quickly, there's a corresponding drop in pressure. So the pressure would be higher here in the stream, and the pressure would be lower here. Just low. Here it's moving faster, and here it's moving slower. When it gets here, water doesn't compress much, so its density isn't changing much. As it's trying to get compressed, that's what pushes it to go faster. Air can be compressed, and so some air can compress there. That would change its density a little. But it speeds up also. So
it's the air when you compress it, your temperature changes, but not.
And that's what you're thinking there. Yeah, if we enclose this, let's say we plug this in, and we're trying to keep blowing air in and cram it in here, it's going to compress, increase its density significantly, and that will increase its temperature. And you remember that because here's your closed container, and you got all the particles, and they're jostling around, right? And this one's moving this way that fast, and this one's moving slower, and this one's going that way, and this one this way. They're random speeds, right? But we know on average, there's an average translational velocity, and that gives us its temperature, right? And so they're moving you fast. If you heat this up, or the other way, compress it by throwing more in there, physically, what are they going to do with each other, their neighbors? They're going to have a lot more collisions. It's going to transfer energy, and they're all going to start moving faster on average. And that increases the pressure. Every time they push against the wall, they hit the wall, they transfer energy and momentum. There's a force. That's what we feel is the pressure. Because remember, pressure was what? Very good. Force over area. So all this force over this area creates the pressure. And that's why we like dealing with pressure. Way back at the beginning of this unit. We were used to forces, and there's a bunch of little forces, but we don't want to track every molecule. You can, but macroscopically, on the big picture, just take the average force over the area, and you can get something called pressure, and we work with that. And just as energy was conserved before, it still is now. We're just dealing with pressures. That's Bernoulli's principle. Another way to think of it here, it's got so much energy here. It's got so much energy here. The total energy has to be the same. If it speeds up, it's got more kinetic energy here, right? Than here. More kinetic. If there's more kinetic, it can't just gain it total. Something else has to have decreased. That was the pressure. It went down.
That's the water pressure?
The pressure in the fluid. In this case, the water or air. Yeah. Yeah. Do you remember we had some tubes? Forgive my mixing of drawings here, but it was over here, the big thing with the air blower. It looked like this. And as we blew air past this, since the pressure's higher here, it pushed down on the water and made the water level go down. The pressure was lower here. See, there's that pressure difference We talked about too. We don't notice many things happen until there's a difference in pressure. So the higher here pushed this down and made this one go up. Because there's less pressure right there. Yeah?
So you said that it lost or it gained kinetic energy. What energy did it lose?
The pressure dropped. The energy associated with pressure. This whole force thing. The equation was, you had, it was basically potential energy, kinetic energy, and energy associated with pressure. And I worked through a derivation, but to skip it all, it ended up being density times gravity times height. Do you see the connection there with mgh? Kinetic energy was density 1/2, density velocity squared. See the connection between 1/2 mv squared? And this was the pressure. That had to stay constant. So it's all kind of in terms of fluid terms, density and pressure. But the gist here was that we're just conserving energy. So if this one increases, this one went down. We also learned from a water tower, remember? If you have water way up high, where's the pressure the greatest? At the bottom. Down here. And then say you do a little hole and it squirts out, right? So it goes from a big pressure, that's what shoots it out, much higher than atmospheric pressure out here. Difference in pressure from high to low shoots it out. So as the pressure changes, so does the speed. If the energy associated with the pressure, it was nice and high at the bottom, and then it shoots out, it drops to atmospheric, well, it's sped up. It makes it shoot out fast. It now has kinetic energy. It's kind of like from potential to kinetic. So that's Bernoulli's equation, its principle. Another example, an umbrella. If wind blows across it, what tends to happen? I'm sure it's all happened to you. You're holding your umbrella, right? And all of a sudden, whoa, you're trying to play Mary Poppins. Why? Pressure. Give me more detail. Yeah, the effect is perpendicular. Good. What effect? What's going on? Give me more details. It speeds up over the top. Thus, there's a corresponding drop in pressure. Excuse me. That's Bernoulli's principle. Yeah, and let's back up even further. Why does it speed up there? Yeah, we're essentially constricting it there. So it's kind of go like this, in a sense. So yeah, it's constricted there. It speeds up. There's a corresponding drop in pressure. So now if you have low pressure here and high pressure underneath, difference in pressure. If you rewrite this equation, as force is pressure times area, that pressure difference is acting over the area of the umbrella. Creates a force. That's what you feel, lifting you up. So anytime a wind, an air, water is flowing past something, this effect can occur. Hey, see, I love how it just all comes together. When we review, we start on one thing and surf along since we're on fluids, right? Any other questions? Let me go back to our very beginning notes here. Chapter 13, liquids. Do you remember what density is, right? At D? What's density? You just love density, right? Mass over volume. Yeah. Big V. Mass over volume. When does something sink or float? We did that, right? Let's see. Say something sinks, float, neither. We had conditions for those. What's one condition you can think of if something sinks? Or just tell me what you know. Shout something out.
Density of the object is greater than the fluid.
If the density of the object is greater than the density of the fluid, then what?
6.
Okay, so we have density of object greater than density of fluid. Yeah, so that's one way to find it out. So we're more dense than, okay, that's not. This book is more dense than water, so if I throw it in water, it's going to sink. Now, you take a big chunk of steel, it's going to sink. What can you do to the steel so it floats? Increase the volume. Very good. And if you do that, what happens to the density? That gets bigger, so this gets smaller. And that's the other condition goes with this one. If the density of the object is less than the density of the fluid, it'll rise up to the top and then stay there. So I think you can gather this one, right? If they're equal, you throw a Ziploc bag completely full of water, get all the air out, throw it in a tank of water, it'll just kind of hover wherever you put it because they're essentially the same density. A fish, right? What's the density of a fish? You know this. It's about the same as water because they're usually floating wherever they want, right? What do they need to do to go down lower? Do they just swim really hard? No, that takes too much energy. They just change their density, right? They got things called air bladders. They can take in a little more air or out. Same with you taking a big breath. You're more likely to float, or it's easier to float. And when you let your air out, I like doing that. Every time I go underwater, I blow a little of my air out. Not all of it, because then it's easier for me to swim at the bottom. I don't have to fight coming back up, or staying down, I should say. All right. How else can we think of sinking, floating? With buoyant force. Good. So give me one.
If the buoyant force is greater than the gravity, or I guess the downward acceleration of the object.
Here's your object. What's that downward force? You know it.
Gravity.
Gravity is an acceleration. Weight. That's what you're looking for. I knew what you meant. I was just helping you. So that's mg. Remember Newton's second law is force equals mass times acceleration. The acceleration here is g. So that's its weight down. And you're saying, and we have a buoyant force up. So if this is bigger, what's happening? I'm ready. Which was which?
If the buoyant force is less than the weight, then it will sink.
Right. Then there's a net force down, correct? Yeah, so sinking is buoyant force is less. I think you can get them now, right? If the buoyant force is bigger, if this is bigger, well, it's going to go up. We did these forces at the beginning of the semester. And if they're equal, it's hovering wherever it's at. What is a ship doing when it's floating in the ocean? Which case do we have? We say it's floating in the ocean. But where's it at? Right? You got the water. Where do ships like to be? Yeah, on the top. So it's kind of like this, right? Which case do we have? Good. We have equal. We say it's floating, but that got it up there. Yeah, now they're equal. Because it's not going up any further, right? And it's not going down. What determines the buoyant force? Remember that?
The weight of the displaced water.
Very good. And the weight of the displaced water. So this ship is displacing this much water, right? Whose principle was that? Archimedes Principle. That's what that was. Yeah. If an object displaces a certain volume of fluid, because I'm taking up this much space, I have to displace that much air. If we weighed that air, that's the buoyant force on me. How does my weight and my buoyant force compare?
Way greater.
Yeah, my weight's a lot bigger than the buoyant force. I have a buoyant force, it's just not enough. When something comes to the top, notice it's not displacing its whole volume of the ship, right? It only needs to displace this much to make those two equal. mg FB. If you push the ship down in a little bit, let's say you add more cargo, right? You put a lot more weight in here. What's going to happen? Exactly. It's going to go down lower. Right? But these are still equal. It weighs more, so now it's more like this. But the buoyant force is increased also, right? Because it's displacing more liquid, more fluid. Remember too, something can have a big buoyant force and not float. Do you remember our examples? Or give me an example, something. What's that?
Submarine.
A submarine, yeah. It can have a huge buoyant force, but it's really heavy. So if it's not enough, it'll go down. Remember our life preservers? That question? If you fill a life preserver full of lead and throw it in the water, what happens? It sinks. Does it have a buoyant force? And it could be a significant buoyant force, big life preserver, but it's not enough to counter its weight. What about a normal life preserver full of styrofoam on you floating at the top on the surface of the water? Who has more buoyant force? The lead life preserver at the bottom or the life preserver you're wearing floating on the surface? Very good, the lead. Because it's completely submerged, so it's displacing a bigger volume. This one doesn't need to displace as much. It's not all the way under the water. Because I'm not as heavy as lead some days. Yeah.
The homework, there was a problem on if you put a fish in a tank of water that's half full and then it's filled to the brim.
Yeah, that's a good one.
So I got the concept, but what if the fish was partially submerged?
So one is like to the brim and the other was like half full, and you throw a fish in, right? If you throw a fish in here, what happens to the water level? It goes up, sure. And how much? Whatever his volume was. Right. He's happy. Will the thing weigh more? Sure, he's now part of the system. There's a buoyant force upward on him. So remember Newton's third law, there's a reaction force to that, and that's pushing down on the scale. That adds to the weight, the overall weight. When you throw a fish in this one, what happens? It overflows, right. How much? The exact same volume. But what happens to the scale now? Why does it stay the same?
Because the water displaced out of the tank is equal to the weight of the fish.
Well put. Archimedes' principle says the buoyant force on this fish is the weight of the displaced fluid. So in order to hold his weight up, which is added to the scale, it needs a buoyant force equal to it. But that water just left. So we're not weighing it anymore. So the two effects cancel. So the weight doesn't change here. Now what you asked was if the fish was halfway? Like this or full?
Full.
Okay. So like this, but the fish is only like this?
Would it be like half of the fish?
Well, let's see. If he's up here, which case do we have? Yeah. So these are still equal, right? Right? So his mg and his FB are the same. He has displaced some liquid, right? But less of it. And that, the weight of that displaced fluid is the buoyant force, which countered his weight. So there'd still be no change. It's just in this case, he didn't need to displace as much to counter his weight. If he's completely submerged, he's displacing more water. He needs a bigger buoyant force, but that all goes over and it balances. Here, he must weigh more because he's displacing more water and has a bigger buoyant force.
So for the other first picture where it's half filled, if it was partially submerged, then it would still increase by not as much.
Right. This is increased by his weight. They're still equal. But yeah, if he was up here on the top, that means he doesn't weigh as much because he didn't need as much buoyant force so it wouldn't go up as much. That's because the fish is probably smaller. Or we're using a fish, but any object like that. Very good. Okay, you're getting this. Okay. And that was pretty much fluids and gases, I think. Remember, more than one thing can happen. Remember our hot air balloon that goes up in the atmosphere? Describe what happens on its way up. It expands. Why?
Pressure changes, so there's less pressure. No, it's not.
Right, if it expands, that means the pressure here must be higher than the pressure here. Why does that happen as it goes up? Is this getting higher or is that getting lower? Yeah, it's getting lower. That's because as you go higher up in the atmosphere, you're higher, right? Pressure is depth dependent. So if you're not as deep in it, you don't have all that as much above you to exert pressure. So yeah, that drops. That means the density is less too. There's less air up there. So yeah, the difference in pressure will make this expand. Will it expand forever? What happens? It reaches equilibrium. But doesn't the higher and higher it go, the pressure drop lower and lower and lower? It does. The higher up you go in the atmosphere, the pressure keeps dropping, but it doesn't expand forever.
That's the question.
There you go. It has to do with the densities. Go back to this. What determines if it floats or not? We can look at it either way. The density of the object is less than the fluid. Well, wait, the density of the fluid, the surrounding air, is dropping, isn't it? It's getting less. The atmosphere, there's less of it. So this is getting smaller and smaller, and at some point, when they're equal, it doesn't go up anymore. Or look at it in terms of buoyant force. It weighs so much. There's an upward force on it. What causes that? How much fluid it displaces. As it goes up, it's getting bigger and it displaces more and more air, right? That should increase the buoyant force, make it go faster and faster. But think about the air it's displacing. There's a lot less of it. So it's really not displacing as much air on its way up. It's physically like bigger, but there's less air it's displacing. So the buoyant force drops. And if the buoyant force drops, they can become equal and it'll stay put. So you got the drop in air pressure, but you also have the fact that it's getting less dense. And they have counter effects. So yeah, a hot air balloon will expand, but at some point it won't just keep going up forever, assuming it doesn't pop. You with me?
So what is the case where it pops? It just keeps going?
Well, that would be if this force, there's a pressure difference, in to out, and it's acting over the area of the balloon. So there's a big force on the balloon. And if the material can't handle it, it'll rip. And bye-bye balloon. So yeah, if you start with this fully inflated and let go of it, it'll try to expand beyond what it's capable of. So they usually start hot air balloons or weather balloons not fully inflated because they know when they go up they're going to get bigger. With buoyancy, I set this up twice and never discussed it, so I figured I'll save it for a review. You guys know what this is? It's a thermometer. Galileo gets credit for this, even though it was somebody else. They have spheres inside. They're full of colored fluid, and they're surrounded by fluid. I don't think any of it's water. It's probably alcohols. But the way you read it is the lowest floating one tells you the temperature. I don't think this one was calibrated very well. It says it's 75. I think it's a little high, but whatever. We're under the lights. That's how you read it. But you can calibrate this. You can use a thermometer this way because when things heat up, they expand. So let's just look at it. We'll take this one. You see the air bubble trapped inside that sphere? If it warms up, that fluid will expand, right? And fill up more of the sphere. So there'll be less of an airspace. What's that do to the density of that sphere, whole sphere? So it's kind of like this. So as it heats up, this expands and it takes up more space. There's less air. Yeah, I want the density of the whole sphere. Because it's closed and sealed off. Have we changed the mass? No. But we have changed the proportion of liquid to air. We've compressed some of that air. The air takes up less space. So overall, it's more full of fluid. It's become more dense. I don't want to draw so from this ratio, the volume of fluid is... Yeah, that's the wrong way to say it, Adam. Yeah, the fluid's taking up more space, but over the whole thing. Let's just go back to the human. Make more sense so I don't confuse you. It's like us with our lungs, right? If you fill them full of air, your overall density does what? It decreases. If you let your air out, your overall density increases. That one probably makes more sense to you. That's what's going on here. It's like letting the air is taking up more or less space. So by squishing the air, it's like letting your air out. And the whole thing overall, there's less air, which is less dense. So we're more full of the more dense stuff. The density overall increases. Just like letting your air out. Does that help?
So the volume has to be changed.
The volume between these two definitely changed. The volume of the alcohol gets bigger, but the volume of the air is getting smaller. And the density of the whole thing includes both of those. This is a lot more dense than this. So if it takes up more space, it's going to dominate. And so by expanding, because it heated up, it becomes more dense. And if it becomes dense enough, more dense than the surrounding fluid, it sinks. And it'll go to the bottom and reveal the next highest temperature. And the reverse happens. When it cools down, it'll contract, the density decreases, and it'll float back up. And that's how you can use this to tell temperature. It's a clever device. And combines all 4 of our chapters. Anyway, these are sold as toys. The last one I have for you then is our thermal imaging camera. You turn it on, open it up. And there we are. Who's that? So this sees outside the visible. Remember, you guys give off radiant energy? It's transferring to this camera through radiation. It converts it to something visible we can tell. So the brighter the spot, the whiter and brighter it is, the hotter it is, the shorter wavelengths it gives off. The darker you see, darker areas are cooler, but they still give off radiant energy. They're just longer wavelengths. And You can see the glasses there. See, they're blocking infrared. So the heat from his face can't get through his glasses to the camera. You can see the same with hair and clothes. Look, see how the nose is slightly darker? That nose is cold. Let's try somebody else. Oh, your nose is even colder. Wave, who is that? Who am I looking at? I think that's you, Ron. Or is that you, Emily? Wave, Emily. Oh, that's you. Oh, hold your hand back up. Look at your fingers. See, you can see blood circulation. Her fingers are colder than her palm. And this can detect that. Differences in temperature. This is fun. Let's get somebody over here. There you are. Is that your arm or the tabletop? It looks cold. Probably the wood table, right? And somebody over here. Hello. Look at the wall. Look at that. It's conduction. You have the faces are hotter, but the gaps in between are cooler because it's conducting heat differently. You can see that a lot in the winter with snow on roofs. Have you ever seen the pattern as the snow melts? Think about it. Where the snow is not, that means heat is conducted better, like the wood joists. The heat's gotten through and melted the snow. Let's see, who's over here? Glasses, good. Doing great. Let's try, let's do this. Let's put it over here. Maybe there-ish. Here we go. All right, what's my method of heat transfer to the wall right now? Conduction, yeah. And which way does it flow? Hot to cold. That's what drives it. So you can see my hand's hot and the wall's cold, but when I remove my hand, see, it's now hot, so it gives off shorter wavelengths. And you can do friction with it, right? You can some eyeballs, maybe a mouth. And there I am. Hey, folks, see my glasses? Take them off. That's how thermal imaging cameras work. They're just picking up the heat transfer through radiation. And things that give off more heat, more radiant energy than they absorb are net absorbers. I mean emitters, and vice versa. So when they're in equilibrium, the temperature doesn't change. Any last minute questions? I think that's all I got for you. Well, email me if you think of something. Have a good day.